When we teach system design, 3 questions make almost every architecture discussion clearer. Will the system stay correct when things go wrong? Will it keep up as traffic and data grow? And can engineers and operators keep changing it without turning it into a mess? In this lesson, we are going to use those 3 questions to build intuition for reliability, scalability, and maintainability. Let's start with the mental model. In practice, we do not build serious products out of one storage engine alone. We mix databases, caches, search indexes, message queues, stream processors, and batch jobs. Once those pieces work together behind one API, we are effectively designing a custom data system, whether we call it that or not. This is the key mindset shift. The real design target is not any single component. It is the end-to-end behavior that users experience when all these pieces interact. A cache miss, a queue backlog, or a stale index can all become part of a system design story. Now let's narrow everything into 3 pillars. Reliability asks whether the system still behaves correctly when hardware fails, software misbehaves, or people make mistakes. Scalability asks what happens when the load changes. Maintainability asks whether the people responsible for the system can understand it, run it, and adapt it over time. Here is a practical definition of reliability. The system should continue to work correctly, even when things go wrong. That includes not only functional correctness, but also usable performance and protection against abuse. Reliability is about preserving the intended service, not about pretending faults never happen. One of the most useful distinctions here is faults versus failures. A fault might be a dead disk, a corrupted response, or a bad configuration change. A failure is when the system as a whole no longer provides the service users need. Good architecture tries to stop local faults from becoming global failures. Hardware faults are the obvious ones. Disks fail, machines disappear, cloud instances vanish. Software errors are harder, because they can be systematic and repeatable, triggered by rare conditions like bad interactions, resource exhaustion, or cascading failures. Human error matters too, because configuration mistakes and operational changes are a major source of outages in real systems. The human error section is especially practical. Do not rely on perfect operators. Instead, reduce the blast radius of mistakes. Use staging environments, gradual rollouts, clear monitoring, and fast rollback paths. Observability matters because teams need early warning signals and enough information to diagnose what is actually going wrong. Now let's talk about scalability carefully. It is not a trophy word. Saying a system is scalable without naming the growth pattern is almost meaningless. The real question is this: if traffic, data volume, or complexity increases in a specific way, what are our options for coping with that increase? The next teaching point is that load depends on the system. A web server may care about requests per second. A database may care about read-to-write ratio. A cache may care about hit rate. Some designs are dominated not by the average case, but by skew, hotspots, and the most extreme users. A social feed is a great teaching example. Read-time timeline assembly makes posting cheap but reading expensive. Write-time fan-out pre-computes timelines and makes reads fast, but celebrities with tens of millions of followers create huge write amplification. The best design often becomes a hybrid because the averages hide the real pain points. This is a key system design lesson. Response time is not one number. It is a distribution. Median tells you what a typical request looks like, but high percentiles like P95 and P99 tell you how bad the tail gets. For user-facing systems, those tail latencies matter because even a small fraction of very slow requests can dominate perceived quality. Now let's connect this to tail latency amplification. Suppose one user request triggers many backend requests. Even if most of them are fast, the end user often has to wait for the slowest important one. So as systems become more distributed, tail behavior matters more and more. When load grows, there is no universal fix. Sometimes vertical scaling is enough. Sometimes horizontal scaling is necessary. Sometimes a few powerful machines are simpler than a swarm of small ones. The important lesson is that stateful distributed systems bring real complexity, so distribution should solve a concrete problem, not satisfy a buzzword. Now let's shift from machine behavior to human behavior. Over time, many people will need to operate, debug, extend, and migrate the system. If the design fights those people, the product will slow down even if the code technically still works. Operability means the system gives teams the information and controls they need to keep it running. Simplicity means removing accidental complexity, especially through well-chosen abstractions. Evolvability means the design can adapt as product needs, scale, regulation, and technology change. That last one matters because no successful system stays frozen. If you remember one thing from this lesson, make it this. System design is not mostly about naming tools. It is about making trade-offs explicit. Name the faults you expect. Name the load that matters. Name the human work required to operate and evolve the system. Once those questions are clear, later architectural choices become far more disciplined.